In this presentation, we will discuss 3 different problems on partial orderings. So without any further delay, let's get started. Which of the following are posets? We have to identify which of these are posets. Okay. Let's first identify whether z equal to is a poset or not. We know that z represents set of integers and equal to is relation defined on set of integers. This means R must be equal to set of all ordered pairs a, b such that a is equal to b. This relation is defined on set of integers. Let's identify whether this relation is a partial order or not. Because if you would be able to determine that this relation is a partial order, then z equal to will be a poset, right? Let's identify whether this relation is a partial order or not. For this, we will first check the reflexive property, that is, a must be equal to a for some a belongs to z of integers, right? We know that a is equal to a, therefore R is reflexive. There is no doubt about this, right? This means a must belong to R, and this eventually means a must be equal to a, and we know that a is equal to a, therefore R is reflexive. Let's identify whether this relation is antisymmetric or not. For this, let's say a, b belongs to set of integers, okay? These are some arbitrary integers a and b. If a is equal to b and b is equal to a, then a must be equal to b. This means if a is related to b and b is related to a, then a must be equal to b. This is according to antisymmetry, right? We know that this is true because in the first place we are saying that a is equal to b. This is given to us. Therefore, a must be equal to b. Therefore, we can say R is antisymmetric, right? Now let's identify whether this relation is transitive or not. Let's say a, b and c, these three are arbitrary integers. If a is equal to b and b is equal to c, then a must be equal to c. This is always true, right? If a is equal to b and b is further equal to c, then a must be equal to c. Therefore, R is transitive. All three properties are satisfied. Therefore, R is a partial order and z, equal to is a poset, right? Now let's identify whether R, less than set of real numbers and less than relation is a poset or not. We know that R is nothing but set of all ordered pairs a, b such that a is less than b. This relation is defined on set of real numbers. We will identify whether this relation is a partial order or not. For this, first we will check the reflexive property. Let's say a belongs to set of real numbers, then a must be less than a according to reflexivity, which is not true. Therefore, R is not reflexive. It is very clear. A is not less than a, right? R is not reflexive. Let's check the antisymmetry. Let's say these two are real numbers. If a is less than b and b is less than a, then a must be equal to b. And let me tell you, this is true. But why? How is it true? If a is less than b and b is less than a, we are saying that a is equal to b. How it can be true? Let's identify. We know that a less than b and b less than a is false. And this is if-then construct, which means implication. A less than b and b less than a implies a equal to b. Premise is false. It doesn't matter what conclusion we have, but false implies anything is always true, right? Therefore, R is antisymmetric. In other words, we can say that if a is less than b, then b cannot be less than a. As simple as that. Therefore, this relation is antisymmetric, right? But this relation is not reflexive, let me tell you, okay? Let's identify whether this relation is transitive or not. And I will provide this to you as a homework. This is your homework, okay? Identify whether this relation is transitive or not on your own. But at the end, we know that this relation is not a partial order and R, less than is not a poset. This is very clear because this is not a reflexive relation, right? Now let's identify whether z, that is set of integers, not equal to relation, is a poset or not. We know that R is set of all ordered pairs a, b such that a is not equal to b. When I say set of all ordered pairs a, b, I'm talking about some arbitrary integers a and b, right? Because this relation is defined on set of integers. Let's identify whether this relation is a partial order or not. For this, we'll check reflexivity. Let's say some a belongs to set of integers, then a must not be equal to a, which is false. Therefore, R is not reflexive. Let's check antisymmetry. Let's say a and b are integers. If a is not equal to b and b is not equal to a, then a is equal to b. Obviously, this is false. In the first place, we are saying that a is not equal to b. Therefore, this cannot be true. Hence, Antisymmetry is not satisfied. Therefore, R is not antisymmetric. This is very clear. Now let's check transitivity. Let's say A, B and C are integers. Then if A is not equal to B and B is not equal to C, then A is not equal to C. Let's see whether this is true or not. It seems like this is true, but let me tell you, this is not always true. Okay, let's identify why. For example, 1 is not equal to 2 and 2 is not equal to 1, but 1 is equal to 1, right? Therefore, if A is not equal to B and B is not equal to C, then it is not always true that A is not equal to C. Here in this example, you can see A is equal to C, right? Therefore, R is not transitive. So it is clear that this relation is not a partial order and z comma not equal to is not a poset, right? Now let's identify whether z comma greater than or equal to is a poset. For this we know R is nothing but set of all ordered pairs A comma B such that A is greater than or equal to B. This is our relation and this relation is defined on set of integers. Let's check reflexivity. Let's say A belongs to set of integers, then A must be greater than or equal to A. We know that A is equal to A, therefore this must always be true. Therefore, R is reflexive, right? Let's check antisymmetry. Let's say A and B are two integers. Then if A is greater than or equal to B and B is greater than or equal to A, then A must be equal to B. This is always true, right? Therefore, R is antisymmetric. Let's check transitivity. Let's say these three are integers. And if A is greater than or equal to B and B is greater than or equal to C, then A must be greater than or equal to C. Is it always true? This is always true, right? If A is greater than or equal to B and B is also greater than or equal to C, then it is obvious that A must be greater than or equal to C. Therefore, R is transitive. Hence, we can say this R is a partial order and Z comma greater than or equal to is a poset, right? Now let's see whether Z comma not divisible is a poset or not. R is nothing but set of all ordered pairs A comma B such that A does not divide B. Right? Let's see whether this relation is a partial order or not. For this, we will check the reflexivity. Let's say A belongs to set of integers. Then A does not divide A is actually false. A divides A, right? Therefore, R is not reflexive. Let's check antisymmetry. Let's say these two are integers. Then if A does not divide B and B does not divide A, then A must be equal to B. But this is false, right? How can this be true always? This cannot be true. Let's see one example. Let's say 2 does not divide 5 and 5 does not divide 2. We know that 2 is not equal to 5, right? Therefore, this is not true. Hence, R is not antisymmetric. Let's check transitivity. Let's say these three are integers. If A does not divide B and B does not divide C, then A does not divide C. This is not always true, let me tell you. Let's see why with the help of an example. We know that 2 does not divide 3 and 3 does not divide 4. But 2 divides 4, right? Therefore, it is not always true that if A does not divide B and B does not divide C, then A does not divide C, right? Therefore, R is not transitive. All these three properties are not satisfied. Hence, we can say this relation is not a partial order and this is not a poset, right? Now, it's time to consider problem 2. Determine whether the relations represented by these non-zero matrices are partial orders. Okay, these are all the matrices given to you. You have to determine whether the relations represented by these matrices are partial orders. Let's take the first matrix. Let's say this is MR and I'm considering three different elements A, B and C that belongs to some set A and relation R is defined on the set A. Okay, and this matrix represents some relation R. Okay. That's why I named it MR. Now let's see whether this relation is reflexive or not. Because we have to determine whether this relation is a partial order or not. Let's check the reflexivity. We know that R is reflexive. We just have to see the diagonal elements here, right? This element represents AA. This represents BB. This represents CC. When AA is 1, this means AA is included in relation R. BB is also there in R and CC is also there in R. All the three ordered pairs are there in R. Therefore, R is reflexive. Let's check the antisymmetric property. R is antisymmetric. Let's see why. If Mij is equal to 1 and Mji is equal to 1, then I must be equal to j. I and j are some indices, right? Or in other words, we can say if Mij is equal to 1, then Mji must not be equal to 1 until I is equal to j. Here you can see that BA does belong to R, but AB does not belong to R, right? AC does belong to R, but CA does not belong to R, right? So it is clear that this relation is antisymmetric. You can clearly see this, right? This element is at index 1, 2, right? And this element is at index 2, 1. You can see that M21 is 1, but M12 is not 1. And you can also see that M13 is 1, but M31 is not 1. Also, M23 is 0 and M32 is also 0. Therefore, it is clear that R is antisymmetric. Okay. Now let's check the transitivity. R is not transitive because M21 is 1, M13 is 1, but M23 is 0. You can see this right here. M21 is 1. Okay. M13 is 1, but M23 is not 1. Therefore, this relation is not transitive, right? So it is clear that R is not a partial order. This relation is not a partial order. Okay. Now let's check whether the relation represented by this matrix is a partial order or not. Let us suppose this is MR and here we have three elements A, B and C. Let's check the reflexive property. R is reflexive. You can see that all diagonal elements are 1. That is why R is reflexive, right? Let's check antisymmetry. R is antisymmetric. You can see that A, B does not belong to R and B, A does not belong to R. You can see that C, A belongs to R, but A, C does not belong to R. Apart from this, B, C and C, B does not belong to R. Therefore, it is clear that this relation is antisymmetric, right? Again, you can see the same thing, right? Now let's check transitivity. Here R is transitive. You can check this on your own. This relation is transitive. Therefore, it is clear that R is a partial order. Now let's check option C. Let's say this is MR. And here you can see all diagonal elements are 1. Therefore, this relation is reflexive, right? Let's check antisymmetry. Okay. This relation is antisymmetric also. You can see AB is 0, BA is 0, right? AC is 1 and CA is 0. Fine. AD is 0 and DA is 1. Fine. Apart from this, BC is 1 and CB is 0. Okay. BD is 0 and DB is 1. And then CD is 1 and DC is 0. Clearly, this relation is antisymmetric, right? Now we can check transitivity. R is not transitive because A, C does belong to R, C, D does belong to R, but A, D does not belong to R. You can see that AC does belong to R, C, D does belong to R, but AD does not belong to R. Hence, it is clear that this relation is not transitive. Hence, R is not a partial order. R is reflexive, antisymmetric, but not transitive. Hence, R is not a partial order. All three properties must be satisfied, right? Now let's consider problem 3. Find two incomparable elements in these posets. These are the posets available with us. We have to find two incomparable elements in these posets. We know this is a poset, right? This is a subset relation defined on power set of 0, 1, 2. And what is power set of 0, 1, 2? This is this set, right? Which consists of phi, a set with element 0, a set with element 1, a set with element 2. And then we have sets with 2 elements. And finally, a set with 3 elements, right? So this is power set of set 0, 1, 2. This relation, subset relation, is defined on this power set of set 0, 1, 2. We know that this is a partial order set and we have to find two incomparable elements in this poset, right? Let's find out. We have to find two incomparable elements in power set of 0, 1, 2. Here two elements A and B are incomparable if neither A is a subset of B nor B is a subset of A. This must be well noted, right? Let's take two sets which are incomparable in this set. You can see that these two sets are incomparable, right? We know that this set is not a subset of this set And this set is also not a subset of this set, which is shown over here, right? Obviously, these two sets are incomparable. Therefore, these two sets are incomparable elements of this poset, right? Now let's see option B. We have a set which consists of these elements, and this is divisibility, right? Now let's find two incomparable elements of this poset. 4 does not divide 6 and 6 does not divide 4. This is clear. These two elements are incomparable, right? You can find other incomparable elements as well. I took these two. You can take any one of these. You can see that 6 and 8 are also incomparable, right? You can select them as well. That is not a problem. You can clearly see that 4 and 6 are incomparable because neither 4 divides 6 nor 6 divides 4. Therefore, 4 and 6 are incomparable elements. Okay friends, this is it for now. Thank you for watching this presentation.